In this video, we'll be discussing geometric probability. Now in basic probability, we generally encounter problems that are discrete. Say for example, tossing a coin or rolling a die. But then there may be some interesting problems. Say for example, choosing a number on a real line or the arrival time of your train. All these variables, they are continuous variables. Now, what geometrical probability does is, it correlates the outcome of sample space geometrically in terms of either length or area or volume depending on number of variables. Now, in one-dimensional geometric probability, we'll have a variable which will take continuous values. Now, what we'll do is, we'll relate these continuous values on a number line. Each and every point on this line segment, it will correspond to an outcome in sample space. Now, in order to find probability of any event A happening, we have to find the length of the interval which corresponds to our favorable cases. Say this length is L. Then this probability of any event A happening will be simply L upon capital L. Now, let us take up an example. Say for example, X is a real number which is chosen randomly from the interval -5 to +5. Now we need to find the probability that x square minus x minus 2 is less than or equal to 0. Now in this case, this variable x, it takes all the values from -5 to +5. So this x, it can be represented by this line segment starting from -5 to +5, where the length of this line segment is simply 10. Now, any point on this line, it corresponds to a unique value of x starting from -5 to +5. Now, we need to find the probability that x is such that x square minus x minus 2 is less than or equal to 0. Now, we'll factorize it. We can write this as x minus 2, x plus 1 is less than or equal to 0. Critical points are -1 and then 2. Now, rightmost is plus. So, this is plus, minus and plus. We need minus. So, this condition is true when the value of x lies between -1 and 2. So, the event is this x must satisfy this inequality, which is x squared minus x minus 2 is less than or equal to 0. And it corresponds to all the values of x when x lies between -1 and 2. So, our favorable region, it corresponds to this line segment from -1 to 2, and length of this line segment is simply 3. So this required probability is this favorable length, which is 3, upon total length, which is 10. So the probability that any real number randomly chosen between -5 and 5 is such that x square minus x minus 2 is less than or equal to 0 is simply 3 by 10. Now in two-dimensional geometric probability, we'll have two continuous variables, and in this case, all the points on the sample space, they'll correspond to some area. So our sample space will correspond to some area, say capital A, and favorable cases, they'll correspond to some area within this given area A. Say this area is simply A. Then this required probability will be given by area of this favorable region upon area of total region. So all we need to do is, we'll just need to find A and A. Now let us take up an example. Say for example, the question is, a square S has side length 30. So we have this square whose side length is 30, and this is your square S. Now it says a standard 20-sided die is rolled. So we have this die which has 20 faces. So outcomes will be 1, 2, 3 up to 20. A square T is constructed inside S with side length equal to the roll. So within this square, we have another square T whose side length, it corresponds to the number on this die. Then it says a dart is thrown and it lands randomly somewhere inside this square S. So when a dart is thrown, it will somewhere land inside this square S. So this is our sample space. Now we need to find the probability that the dart also lands inside this square T. So we have to find this probability that this dart, it lands inside this small square. Now the probability that this dart, it lands inside this square T, it depends on the area of this small square. And the area of small square, it actually depends on length of the side, which depends on the number on this die. Now, if the die results in K, then the probability that the dart also lands inside T, if the number on the dice is K, is given by this favorable area, which is area of the square, and area of the square will be simply K square, because in that case, length of this side is K upon this total area, which is 30 square, and that is 900. Now we need to find probability that for all such cases, this dart, it lands always inside the square T. So this probability, it will be equal to this probability Pk into probability of T by K, where the value of K varies from 1 to 20. Now what is probability of K? Now probability of K is, out of these 20 numbers, the die has rolled K. Now this die, it can roll any number from 1 to 20 with equally likely probability of 1 by 20. So this probability of K is simply 1 by 20. So this is summation K varies from 1 to 20 and will be 1 by 20 into K square by 900. Now we can write this as 1 by 18000 into summation K square, where the value of K varies from 1 to 20. So it will be 1 upon 18000 into, now this is n plus 1, 2n plus 1 by 6. So it will be n plus 1, 2n plus 1 whole divided by 6. Now here this 0 will cancel. This is 3. This is 7. So it is 287 divided by 1800. So the probability that this dart, it also lands inside the square T is 287 by 1800, and that is the answer to this question. A very interesting question in two-dimensional geometric probability is, if we have a pencil of length L, now we have to find the probability that in how many ways we can break the pencil in 3 parts so that these 3 parts, they form a triangle. Now long back, I have already made a video on that question. So what I'll do is, as of now, I'll provide the link to that question in the description below. Now when we have 3 continuous variables, then in that case, this sample space, it can be geometrically represented by a 3-dimensional volume, say capital V. Now for any corresponding event, we'll find this favorable volume, which is say small v, then this probability, it is given by small v upon capital V. Now let us take up an example. Say for example, the question is, Alex, Bob and Charlie each randomly pick a real number between 0 and 1. What is the probability that sum of the squares of their numbers does not exceed 1? Now each of them, they can pick a real number between 0 and 1. For Alex, this choice, it is suppose represented by this variable x, which can take any value from 0 to 1, which can be represented by this line segment. For Bob, suppose it is represented by y, and again it is a line segment of length 1. And for Charlie, say it is z, which again is a line segment of length 1. Now all the possible combinations of their choices, they can be represented by this cube of unit volume. Say this is x, this is y, and this is z. Now x can take any value from 0 to 1, y can take any value from 0 to 1, and z can take any value from 0 to 1. And all the possible combinations of x, y and z, they are represented by points lying on or inside this cube of volume 1 unit. So volume of this cube is simply 1 cubic unit. Now we need to find the probability that sum of squares of their numbers does not exceed 1. So that means x square plus y square plus z square, it is less than or equal to 1. Now we know that x square plus y square plus z square equals to 1. It is nothing but a sphere of radius 1 unit. And here we are talking about x square plus y square plus z square. It is less than or equal to 1. So that means we are talking about all the points on or inside the sphere in this first octant where x, y and z, they are all positive. We have to calculate our favorable volume. Now first what we'll do is we'll find volume of the sphere, and volume of the sphere is 4 upon 3 pi r cube, and r in this case is 1. So it'll be simply 4 pi by 3. Now this sphere, it is symmetrically distributed across all the 8 octants, and we just need the volume of sphere in the first octant. So this required volume or our favorable volume will be simply 1 by 8 into 4 pi by 3, and it will be simply pi by 6. So now we have our total volume and our favorable volume. So this required probability, it will be simply pi by 6 by 1, and which is simply pi by 6. Now here the question is, a bus arrives at a station every day at a random time between 1 p.m. and 1:30 p.m. A person arrives at the station at 1 p.m. and waits for the bus. If at 1:15 the bus has not yet arrived, what is the probability that the person will have to wait at least an additional 5 minutes? Now this bus, it arrives at a station every day at a random time between 1 p.m. and 1:30 p.m. So the time of arrival for this bus, it is random, and it is a continuous variable which lies between 1 p.m. and 30 p.m. So we'll consider this length as 30, taking 1 unit for each minute. All the points on this line, they correspond to any random time of arrival of this bus. So our entire sample space, it can be geometrically mapped with this line of length 30. Now here we need to find the probability that person will have to wait at least an additional 5 minutes if it is given that at 1:15 the bus has not yet arrived. So we'll define two events. Event A is person will have to wait at least an additional 5 minutes. And then event B is at 1:15 the bus has not yet arrived. The bus has not yet arrived. Now we need to find this conditional probability that this person has to wait at least 5 minutes if it is given that the bus has not yet arrived at 1:15. So this conditional probability P upon B is actually P A intersection B upon probability of B. Now first we'll calculate probability of B. Now probability of B is at 1:15 the bus has not yet arrived. So if the bus is not here at 1:15, so say this time interval is 1:15, this bus, it will be expected at any time between 1:15 and 1:30. So this probability that the bus has not yet arrived at 1:15, it is given by this favorable length, which is 15, upon total length, which is 30. So this probability is 15 by 30, which is 1 by 2. Now we'll find this probability P A intersection B. It is given that at 1:15 the bus has not yet arrived and the person will have to wait at least an additional 5 minutes. So that means now it corresponds to the case where this bus arrives after 120. So if the bus arrives after 120, this person has to wait at least an additional 5 minutes. So now in this case, this bus, it must arrive after 120. So in this case, this favorable case, it corresponds to this interval of length 10. So this probability, it will be simply 10 by 30, which is 1 by 3. Now this conditional probability PA upon B, it will be PA intersection B, which is 1 by 3 upon probability of B, which is 1 by 2. So the required probability is simply 2 by 3, and that is the answer to this question. Today we'll discuss an interesting problem in geometrical probability. And the question goes like, if you break a pencil in 3 parts, what is the probability that the 3 parts can be arranged to form a triangle? Suppose we have this pencil, and suppose length of this pencil is L. Now we have to break this pencil in 3 parts. Suppose these are the 3 parts. Now suppose length of this first part is X, length of this second part is Y, and length of this third part will be L minus X minus Y. Now first we'll find uniform sample space for this given condition. So we know that this X, it should be greater than 0 but less than L. In the same way, Y also should be greater than 0 but less than L. And the third one, which is 0, is less than L minus X minus Y, and it should be less than L. Now here we know that X and Y, they are both positive. So from the third one, we'll get this condition as X plus Y is less than L. So we have 3 conditions. So X should lie between 0 and L, Y should lie between 0 and L, and X plus Y should be less than L. So we'll plot this region on a coordinate plane. So X, it takes the value from 0 to L. In the same way, Y takes the value. So this is X and this is Y. So Y takes the value from 0 to L. So we have this region, which is this square. And then this third condition, which is X plus Y is less than L. So I'll draw this line, which is X plus Y is equal to L. So it'll be the straight line passing through these 2 points. And then X plus Y is less than L. So if I'll put origin, so 0 is less than L, which is true. So that means we can break this pencil in 3 parts whose sample space can be represented by this uniform area, and which is area of this triangle. Now we need to find this condition that these 3 parts, they can be arranged to form a triangle. Now let 3 sides of a triangle be A, B and C. Now we know that A, B, C are sides of a triangle if they satisfy triangle inequality, and triangle inequality is sum of 2 sides is greater than the third side. So that means A plus B should be greater than C, B plus C should be greater than A, and C plus A should be greater than B. Now I will take A plus B. So what is A plus B? A plus B is X plus Y should be greater than L minus X minus Y. So from here I'll get X plus Y should be greater than L by 2. Now from the second one, B plus C is greater than A. So what is B? B is Y, and this is plus L minus X minus Y. It should be greater than X. So here Y will cancel. So here I'll get X should be less than L by 2. And from the third one, C plus A, C is L minus X minus Y plus X, and it should be greater than Y. So here I'll get Y should be less than L by 2. So the condition that these 3 parts, they can be arranged to form a triangle is this X plus Y should be greater than L by 2, X should be less than L by 2, and Y should be less than L by 2. So I'll mark this region. So I'll take X as L by 2. So this is X is L by 2, and then I'll also have this Y equals L by 2. So here x should be less than L by 2 and y should also be less than L by 2. So we have this square. And now this third condition is x plus y should be greater than L by 2. So first I'll draw this line, which is x plus y equals L by 2. Now this point is L by 2 comma 0. This is 0 comma L by 2. So I'll draw this line. So this is x plus y equals L by 2. Now if I'll put x and y as 0, I'll get 0 is greater than L by 2. So that means 0 doesn't satisfy this equation. So the area or the region that we'll need is above this line. So the condition that these three parts can be arranged to form a triangle corresponds to this blue triangle. Now we'll calculate this probability that these three pieces, they'll form a triangle. So what is the favorable area? Favorable area is this area of blue triangle. So this is half. Now what is the length of this side? So it is L by 2 and this also is L by 2. So half L by 2 into L by 2. And then what is the total area in the problem? Area of this black triangle, so which is 1 by 2, and then length of this side is L. This side is also L, so that is L into L. So half will cancel, L will also cancel. So this is 1 by 4. So which simply means if you have a pencil and if you randomly break it in three parts, then it is 25% chance that these three pieces will form a triangle. Now here the question is, two numbers are chosen randomly and uniformly from minus a to plus a. What is the probability that absolute value of the smaller number is greater than 2 times the absolute value of the larger number? And does this final answer depend on the value of a? Now suppose the two numbers are x and y and they belong to this set from minus a to plus a. Now all the points on the sample space, they'll correspond to all the points inside this square of length 2a. So this is your x and this is y. This is minus a comma 0. This is a comma 0. 0 comma a and 0 comma minus a. Now it says, what is the probability that absolute value of the smaller number is greater than 2 times the absolute value of larger number? So we'll have two separate cases. Case 1, when x is the smaller number, that is when x is less than 1. Now first we'll mark this region. So we'll have this line y equals x line. Now when x is less than y, we are talking about all the points which lie above this line. Now we have this condition that absolute value of the smaller number, that is mod of x, it should be greater than 2 times mod of y. Now in the first quadrant, we'll have this condition that x is greater than 2y. So we'll draw this line, y equals x by 2. So this point will be a comma a by 2, and then we'll take the transformation of mod x, and then we'll take the transformation of mod y. So here our favorable region is this triangle. Now in the same way, we can take the second case when y is greater than x. In that case, we'll have this condition that mod of y is greater than 2 times mod of x. Now in this case also, from symmetry, we'll say this area will correspond to this similar area. So this favorable area, it will be simply 2 times and then 1 by 2. And what is the area of this triangle? Area of this triangle will be simply a square. So our favorable area will be a square. Then this required probability will be favorable area upon total area, which is 4a square, and which is nothing but 1 by 4. So the probability that the absolute value of the smaller number is greater than 2 times the absolute value of the larger number is 1 by 4. And the final answer, it doesn't depend on the value of a. Now another interesting problem in two-dimensional geometric probability is, last night Dave and Kathy both arrived at Pizza Palace at 2 different random times between 10 p.m. and midnight. They had agreed to wait exactly 15 minutes for each other to arrive before leaving. Now what is the probability that Dave and Kathy were together at pizza place last night between 10 p.m. and midnight? Now there are two people, Dave and Kathy, and they can randomly arrive at this pizza palace starting from 10 p.m. till midnight, that is 12 a.m. Now their arrival, it can be mapped with a line segment of length 120 units, 1 unit each for every minute. Now since we have two variables, one for Dave and one for Kathy. Now how do we write the sample space of their arrivals? Since we have two variables, so we can represent this sample space as this square of length 120 units, represented by these variables x and y. Say x is for Dave and y is for Kathy. Now any point inside this area, it corresponds to arrival times of Dave and Kathy. Now this point, it corresponds to the time where both Dave and Kathy, they arrive at Pizza Palace at 10 p.m. Now this point, it is 120, 0. So it means that in this case, Dave arrives at 12, whereas Kathy arrives at 10 p.m. So all the possible outcomes, they can be mapped to this area, which is say A, and it'll be simply 120 into 120. Now it says they had agreed to wait exactly 15 minutes for each other to arrive before leaving. Now what is the probability that they were together at Pizza Palace? Now they'll be together if and only if the difference between their time of arrival is 15 or less than 15, because they have agreed to wait exactly 15 minutes, not beyond that. So our favorable case will be when the value of x minus y is less than or equal to 15. So if their time of arrival, it is spaced 15 or less, then they'll be together. And if it is greater than 15, then they'll not meet. So we have to find this probability that they were together. That means this mod of x minus y, it should be less than 15. Now we can write this as minus 15 is less than equal to x minus y is less than equal to plus 15. Now we'll represent these two areas. Now the first one is x minus y is greater than equal to minus 15. Now for this case, we'll draw this line x minus y equals minus 15. Now when y is 0, x is minus 15, and when x is 0, y is 15. So it'll be this point and somewhere here. So it'll be this line. This point is 0, 15. For this case, it'll be x minus y, it is less than 15. So we'll draw this line x minus y equals 15. And in this case, when y is 0, x is 15. And when x is 0, y is minus 15. So it'll be this line. Now we'll put both x and y as 0. So we'll get 0 is greater than equal to minus 15 but less than plus 15. So that means 0 lies in this region. So our favorable region is this region of the square which lies in between these two lines. So our required probability is area of this red portion upon area of this square. Now first we need to find area of this red portion. Now from symmetry we can say that these two areas, they are equal. Now what is the length of the side of this triangle? Now this length will be 120 minus 15. So it will be simply 105. And from symmetry we can say this length is also 105. So area of non-shaded portion, it will be 2 times 1 by 2 into 105 into 105. Now this 2 and 2, it will cancel. So area of this shaded region, it will be simply area of this square, which is 120 square minus area of this non-shaded region, which is 105 square. And this area, it will be a plus b into a minus b. Now a plus b will be 225 and then A minus B will be simply 15. So area of this region is 225 into 15. Now we need to find the probability that they were together. So this probability, it is given by this favorable area, which is 225 into 15 upon total area, which is 120 into 120. So this is 5 and 8. And here also we can cancel with 15. So this is 15 into 15 and this is 15 into 8. So this value will be simply 15 upon 64. So the probability that Dave and Kathy, they were together is simply 15 by 64. And that is the answer to this question. If three real numbers are chosen randomly and uniformly from 0 to 1. So suppose three real numbers are X, Y and Z. And they take the value from 0 to 1. Now the sample space, it can be mapped with a cube of unit volume, now this is X, this is Y and this is Z. Now this is 0, 1, 1 and 1. Now it says, what is the probability that the square of one of the numbers will be greater than sum of the squares of the other two numbers? So suppose we have this first case when, say, x square plus y square, it is less than z square. Now we look at different possibilities by taking different values of z. Value of z starts from 0 and then it goes all the way up to 1. So when the value of z is 0, it represents all the points inside this point circle. And if z is equal to 1, then x and y, they'll correspond to all the points inside the circle whose radius is 1. So at 1, we have this circle. So this is the region. And at 0, there is no point. At any general point, z equals r, we'll get this as x square plus y square and it'll be less than r square. So at any z which is equal to r, it'll represent this portion of circle with the radius r. Now z, it varies from 0 to 1. So if z varies from 0 to 1, this actually will represent 1/4 of a cone. 1/4 of a cone of unit radius and unit height. So this favorable volume will be given by 1/4 and will be 1 upon 3 pi r square h, and which is simply pi by 12. Now we'll have three such cases. Second case, when x square plus z square is less than y square, and this third case when y square plus z square is less than x square. So total favorable volume will be given by 3 into pi by 12 and there'll be simply pi by 4. So this required probability is simply pi by 4 divided by 1, and which is pi by 4. Now here the question is, we need to find the probability that the 3 points on a circle will lie on a same semicircle. So if we have a circle, then we have to find the probability that if we choose any 3 points, say A, B and C, they will lie on same semicircle. Now how do we solve this question? So what we'll do is, we'll assume the circumference of this circle is say 1 unit. So it is still a general case, and what we'll do is, we'll cut this circle at A and we'll spread it out as a line. So we can write this as this line A. Now this point again will be A and this length will be 1 unit. Now we'll choose 2 points B and C on this line which are at a distance of x units from A. And suppose the midpoint of this line, which corresponds to diametrically opposite point across A, and this distance is 1 by 2. Now clearly the value of x and y, it will lie between 0 and 1. So this entire sample space, it can be expressed as the square of area 1 unit. So this is 0, 1 and 1. This is x and say this is y. And all the points in this square, they'll correspond to different positions of B and C. Now it says we have to find this probability that these 3 points, they lie on the same semicircle. Now there will be 2 cases. Case 1, when B and C, they lie on same side of M. If they lie on same side of M, then in that case, both x and y, their value should lie between 0.5. So this probability they lie on same side, it will be simply 1 by 2 into 1 by 2. Now they can lie on either side of M. So we have to actually multiply it with 2. So this probability will be 1 by 2. So the probability that these 2 points, they lie on same side of M is 1 by 2. So if they lie on same side of M, they lie on the same semicircle. Now another possibility is when B and C, they lie on opposite side of M. Then in that case, you have to find conditions on X and Y. So the second case is when B and C lie on opposite side of M. Now this distance from A, it is X, and this distance of C from A in that case will be 1 minus Y. So this distance is X and this distance is 1 minus Y. Now they lie on the same semicircle if X plus 1 minus Y, it is less than 1 by 2, because it has to lie in the semicircle, and we are talking about this case when the value of X is less than Y. So we have this first case that Y minus X, it is greater than 1 by 2 when X is less than Y. So we'll mark this region. Now first we'll mark X equals Y line. So this is X equals Y line. Now X is less than Y. We are talking about this region. Now in this region, we have to find region corresponding to this inequality. Now when the value of X is 0, value of Y is 1 by 2. And when value of Y is 0, value of X is minus 1 by 2. So it will be this line. Now if we put this point 0, 1, it satisfies this condition. So we are talking about this region. So this is the region that we get from this condition. Now we'll also have the second case when X is greater than Y. Now if X is greater than Y, then in that case, we'll get this condition that Y plus 1 minus X, it should be less than 1 by 2, which is X minus Y is greater than 1 by 2. Now if we draw this region, it will be this symmetric triangle. Now below this Y equals X line. Now this is 1 by 2. Area of the shaded region will be 1 by 2 into, now this length and height will be all 1 by 2. 1 by 2 into 1 by 2, and then the second area will be same as the first. So this area will be simply 1 by 4. Now the probability that B and C lie on opposite side of M, but still they lie on a semicircle. So this probability when they lie on the opposite side, it will be simply 1 by 4. So combining these two cases, we'll get the probability that they will lie on same semicircle. It will be simply 1 by 2 plus 1 by 4, which is 3 by 4. So if we choose 3 points on a circle, the probability that they lie on the same semicircle is 3 by 4. Now the question is, A point Pxy is selected at random inside the square with boundaries x equals 0, y equals 0, x equal to 4 and y equals 4. So we have our coordinate axis and then we choose this square of length 4 units. So this is 0, 0, 4, 0, 0, 4 and 4, 4. Now this is a question of geometrical probabilities. So the area corresponding to this entire subset will be equal to area of the square, which is 16. Now we need to find the probability that the point P is inside the parabola y square equals x. Now y square equals x. Now when x is 4, y is 2. So it will be this parabola y square equals x, and we have to find the probability that this point lies in this area. So number of elements in this set, it is equivalent to area of this curve from 0 to 4. So we can write this as this integral from 0 to 4 and then y dx. Now this is from 0 to 4 under root x dx. So it will be this x to the power 3 by 2 and this is 2 by 3 from 0 to 4. Now this is 2 cube. So it will be this 16 by 3. So now this required probability is favorable area 16 by 3 upon total area, which is 16. So it will be this 1 by 3, or we can write this as 3 by 9. So the value of k is simply 3. And that is the answer to this question. Now question number 3, part A is, let x be chosen at random from the interval 0 to 1. What is the probability that greatest integer function of log 4x to the base 10 equals greatest integer function of log x base 10. Now they are equal, and suppose they are equal to some number, say r. Now when greatest function of x is equal to r, then x lies between r and r plus 1. So for this first part we can write this log 4x to the base 10, it will lie between r and r plus 1. Now if we take anti-log, we can write 10 to the power r divided by 4, it will be less than or equal to x, and it will be less than 10 to the power r plus 1 divided by 4. And the same way we can write it for the second part. Again this log x base 10 will lie between r and r plus 1. So it will be greater than 10 to the power r but less than 10 to the power r plus 1. Now there is an AND condition between these two results. So if we take intersection of both the conditions, we'll get x should be greater than 10 to the power r, but it should be less than 10 to the power r plus 1 by 4. Now we can write 10 to the power r plus 1 by 4 as 5 by 2 into 10 to the power r. So these two greatest integer functions, they'll be equal when x lies between 10 to the power r and 5 by 2 10 to the power r. Now if we find length of this interval, say LR, then length of this interval LR will be 5 by 2 10 to the power r minus 10 to the power r, which is 3 by 2 into 10 to the power r. Now we have to find length of all such intervals for which the value of x will lie between 0 and 1. So this x, it must lie between 0 and 1. Now 10 to the power r, it is greater than 0 for all r belongs to r, and then 5 by 2 10 to the power r will be less than 1 if 10 to the power r, it is less than 0.4, that is when the value of r is less than or equal to -1, where r is an integer. So from these two conditions, we'll get this r will take the value starting from -1, -2, -3 up to -infinite. Now we need to find this required probability. Now for this probability, the sample space, it corresponds to length of this interval. So length of sample space, it is simply 1. Now we need to find our favorable length, which corresponds to all these cases. So our favorable length L will correspond to this summation LR, where R varies from -1 to -infinite. So it will be 3/2 10 to the power -1 plus 10 to the power -2 10 to the power -3, and this series will continue up to infinite. Now this is nothing but a GP. So it will be 3/2 A upon 1 minus R, which is 3/2 into 1/9, which is 1/6. So from geometrical probability, we can say that this required probability of this event, say A, is given by small l upon capital L, which is 1/6 upon 1. So this required probability is 1/6.